stochastic dominance with non-response. Rami is doing some very interesting work, and I'm very happy that he did to give this talk that late in an hour in Australia. He is in Melbourne at the moment. So Rami, this is about an hour, perhaps a bit over an hour. And if it's okay, we can interrupt with questions, right?
Of course.
Take it away.
Thank you again for inviting me to present in your seminar series. I hear great things about it, and now you have a YouTube channel. Awesome. So today I'll be talking to you about a co-authored work with on stochastic dominance testing, but excuse me, in the presence of survey non-response of any form. And the applications we have in mind here are the comparison of ordinal random variables. So we're looking at, for example, Likert type responses and comparing those types of distributions from them. Now, it's a co-authored work, and I don't know, some of you might know my co-authors. There's a Lebanese, Canadian, and Australian connection, so something trans-hemispheric, I guess. So we are all Lebanese and Canadian, in fact. We've all overlapped in Montreal or Quebec City, or even at some point in, of course, Beirut. The application was driven mostly by my colleagues who, like me, also are very passionate about what's happening to Lebanon, being all of us Lebanese. I don't know if you've been following, but it's quite a horrible situation over there. And this is what also struck up the idea of having an application on comparing trust levels in Lebanese public institutions. So let's talk a bit about that then, for some background first. So stochastic dominance comparisons of these distributions now for ordinal random variables arises quite frequently in practice. And salient examples of these types of comparisons are where one wants to compare, I guess, the ordinal distributions for self-reported Likert type scale responses from surveys. So think of, for example, a survey you ask someone to participate in the survey, and they have to report on some numerical scale, let's say their level of happiness, or their level of trust in a public institution, or their health status is another example. So it's the coverage of applications is quite wide, I would say. And as anybody who has worked with survey data of this sort, we all know the specter of non-response is here to haunt us. It's a universal problem in all surveys. And so the problem is that participants just choose to not respond, meaning that they choose to entirely not want to participate in the survey, or they might participate but not answer various questions. These are different types of non-response, which are unit and item non-response respectively, which we're not going to make a point of separating the two kinds here. We're just looking at non-response across all kinds here. And the real problem here or what creates real problems is the fact that non-response destroys the point identification of the distribution of interest or distributions of interest. And so, sorry, I went too fast there. And so what does one do typically in practice? Now, there's a large body of literature that developed primarily by statisticians, and those especially, if any of you guys know about the kind of work that's taking place by statisticians at University of Waterloo or Carleton in Ottawa, they do a lot of work with missing data, but the kind of practice that they do over there is to work with imposing assumptions that implement that weights of some sort, survey weights, where you can treat missingness or non-response as being missing at random or missing completely at random. This is in the vein of like famous works of like Don Rubin and others. But one thing we do understand, though, is that such types of assumptions are really unverifiable in practice, especially if you're going to do this stuff with imputations, right? And so you set up the wrong type of imputation or you implement the incorrect assumption, then what happens is that could lead to biased inferences due to misspecification. And so essentially, what's the way forward? You could stick with this method of imputation, but what we're going to do in this work here is go forward by using methods of partial identification. And so just so that we're all on the same page about what that is, I'm going to illustrate with an example based on the empirical application of the paper. So
somewhat related to this, to the structure of missing data, most of them usually concentrated in the right tail, as I understand.
I see. So I agree with you when you're thinking about applications, say, with income data, right? So in the question, so the application that I'm looking at over here, it doesn't cover that type of example. Here we're looking at ordinal distributions. So I would say an example of which is basically like what's on this slide. So it's the data is categorical, right? And so it's not quantitative. And so we don't have issues of the tails for this reason. However, in a working paper that will come out soon, I have worked with a student to deal with that type of missingness issues with quantitative data. So the extension of the ideas in this paper to that setup. Yeah, I agree. This is
and if it's indeed in the right tails in income, that rules out randomness for missing, right?
Right, because it's of course non-random type of missingness, right? If you have systematic missingness of that the rich are missing from your data set, and you want to say study or you want to work with a device that does inequality comparisons, then excluding the rich is going to bias everything. Right, so that would be essentially the intuition behind that, right? So if you have non-systematic missingness, then you have to account for it in some way, and the ideas that have proliferated in much of statistics as opposed to econometrics is to deal with this through imputations. So they would develop mathematical and statistical models that would try to predict what would be the appropriate value to put in for what is missing. And of course, this comes from some prior belief about what is causing missingness. And but if you get the model wrong, or like you incorrectly specify it, then all inferences that are predicated upon it will then be false or subject to biases. And to what extent are these biases really a problem? You can't really know. So unless you know the truth, but then if you know the truth of what's causing missingness, then what's the issue to begin with? And so here, though, we are looking at categorical data, which is not covered, does not intersect with the setup that you've mentioned, the important setup that you've mentioned. Okay, I hope that answers your question. The example here that we'll use to illustrate what we mean like with ordinal data, so it's really categorical. And so here with, let's say, trust levels, that comes from survey data. So there are various organizations in Lebanon that ask people to participate in surveys where they ask them, for example, individuals to report their level of trust. They say in a questionnaire, what is your level of trust in, say, the Lebanese government? You could have to pick a category, not at all, not very much, a lot, or a great deal. Now, typically, when one wants to work with these types of data, a numerical scale is imposed on it. But just before I get into the issue of numerical scales, I just want to point out how much of an issue non-response really is. I mean, with this survey from the World Values Survey, pardon me, in 2013, the non-response frequency is 18%. That's quite large. It's not like 1%, 2%, and this is very, very big. And it's
I can tell you that the census non-responses in earnings data is a third of the data, 30% and above.
Yeah, sure, but I mean, it's not. So I was about to say it's not uncommon, right, to have this, and this then begs the question of how do we account for what is going on with the data, right? And how do we try to do inferences that is robust to whatever may be causing missingness? And so think about, for example, here with the government data, people might not want to respond because they might fear reprisal from their government, or they might not want to respond because they just feel lazy. There could be many reasons, right, for that. And so there's heterogeneity in the non-response. Now, trying to model these things sounds like a daunting task. So imputation, I would not say that imputations is the silver bullet here, right? It's at best some approximation, which could be really bad. So what I wanted to point out also is that with these types of Likert responses, there's a numerical scale. And here, for example, you could put the scale 1, 2, 3, 4, right? You can put other numerical scales like 5, 6, 7, 8, or you can change them in whatever way you want. And if you're doing distributional comparisons, which I'll get to in a minute, a little bit later, you want to do comparisons that's invariant to the numerical scale, so scale independent. And that's why you need stochastic dominance. So that's where we're going with stochastic dominance. But let me just continue here for a moment about partial identification. So just to show you what we mean by that so that we're all on the same page. So if we adopt the numerical scale 1, 2, 3, 4 for the categories where 1 is for not at all, 2 for not very much, 3 for a lot, and 4 for a great deal, then what you're going to see by just applying the law of total probability to expand the unconditional CDF F13S, that's just the CDF of this ordinal variable, you can decompose it by conditioning on response and non-response as this mixture. What you do not really observe, of course, or cannot estimate is this fella right there. And so that's what's going to basically mean that you cannot point identify the object of interest. And so what you can do, though, essentially, is try to develop bounds on this object of interest. So the way to go about doing that is starting off from the case where, let's say, we are completely agnostic about what is causing missingness or non-response, pardon me. If you're in that setup, the only thing you can really deduce is that the conditional distribution that is not observable, because it's conditional on non-response, it's just sandwiched between 0 and 1. This is like goes back to the Chukmansky way of bounding these distributions of non-observables. And so if you substitute these bounds into the representation of the unconditional CDF, you'd obtain what is called the worst case bounds that are reported on the second bullet point. And so what you can do with these bounds is you can easily, of course, estimate them. They're only a function of observables, right? So everything here, in principle, you can estimate. And you can use sample analog estimators, plug-in estimators, whatever you like. And so what this is essentially what's also called the identified set. So this captures all the information about the values that are, I guess, they are observationally equivalent with the true CDF F13, right, at each point S. And so we could estimate it. And here is a plot of that.
Excuse me, is it essentially from Fréchet-Hovding bounds?
So Fréchet-Hovding bounds are bounds on a joint CDF, which is particularly a copula, right? So those are the worst case bounds for a copula. Here we don't have a joint distribution. We have a univariate distribution. And so this is essentially sort of, you could say, the analog of that in here. So this is just by substituting in these inequalities into the law of total probability expansion, you would then rewrite it to get these two bounds on this guy. So they are the worst case. I'm sorry?
Conditional distribution. F13 is conditional distribution, right?
No, so F13 is unconditional. These are the conditional ones, where it is conditional on response and non-response. Sorry, conditional on response, pardon me, in this case. So we substituted out F13 conditional on non-response, because it's just sandwiched between 0 and 1. And we substituted out using these bounds to get what is given in these inequalities in the second bullet point. So those bounds are estimable, right? Because they're a function of only observed objects. So P1 is the probability of response, and F13 conditional on response is basically work with the data that you have of responders, and then you can just use the empirical distribution function, for example, to estimate it. So those objects are point identified, but it's the unconditional one here that isn't. And so here is an estimate. Sorry, here I report the estimate of the bounds with this data set. And you can see that how wide how far apart these two CDFs are basically is a function of how much non-response there is, the frequency of non-response. And so the larger the amount of non-response, the wider or more far apart they are, and hence the wider is the identified set, meaning the less, more badly identified it is. So this is essentially the illustration of just what we mean by partial identification with bounds. I'm going to make use of these bounds in a way to carry out distributional comparisons. That's where I'm going. So, so now with this illustration in mind, this brings me to the kind of questions I'd like to, that are of interest in this work. So the backdrop here is, suppose there are two CDFs, F1 and F2 of an ordinal variable, supported on the same numerical scale. And what we're interested in doing in this paper is inferring that a strict stochastic dominance between F1 and F2 of the following form. This holds for all the categories except the top category. At the top category, F1 and F2 are both equal to 1 because they're CDFs. So we want a strict inequality as well. And so what this strict inequality between these two CDFs really is saying is that F1 dominates F2 stochastically and strictly at the first order. Now, why do we care about having that device for ordering distributions? Because in the practice of comparing ordinal distributions, the value of this is having scale independent comparisons of means of these distributions. So what this is essentially the advantage here, is that the mean of F1 will then be strictly bigger than the mean of F2, whatever is a numerical scale you use. Because after all, the intuition here is just that you are comparing the ordinates, right? The ordinates are scale invariant, right? So, and that's essentially where what buys you the comparison to be scale independent. Now, okay, that's how people are using stochastic dominance in this literature. But like I said, there is missingness in the data, and how then does one carry out comparisons, right? In presence of missing data. So to formulate it more carefully, the question being asked is, using survey data on ordinal variables, how do we test for stochastic dominance of the form described above that is robust to survey non-response of any form? So that's the catch, because you will have data on the two populations, but you have missingness within these data sets due to non-response, say. And then you want to carry out a comparison of the objects that you are not point identified, right? The unconditional F1 and F2. Right? And how do we do that comparison in a manner that is robust to whatever is causing messiness? So that's what the paper is really all about. There are, of course, we put forward a methodology in doing so, and there are, of course, some serious challenges in getting to the answer. For example, some of the challenges we faced here is that while there is this really large body of literature on stochastic dominance testing, and I have contributed to that literature myself, and so the problem is that the data sets that come out for these ordinal data, with these Likert type responses, are basically complex survey data. They're not IID, simple random samples, or time series, where a lot of these statistical tests for stochastic dominance have been developed for. So there is developing tests for stochastic dominance with this very complex type of sampling is still a gap in this literature. But that is not really the most important or most difficult hurdle to cross or jump over. The more difficult one is the one where these tests for stochastic dominance, while they've been around for decades, people have been developing these for decades, they only apply to scenarios where you have complete data, meaning no missingness. It's the hunky-dory situation, right? You don't have to worry about missingness. Your data is perfect, and so you can do comparisons. If you don't have data, if you have incomplete data, like here because of non-response or missingness, the standard technology for doing or standard testing procedures do not apply. And so here we're breaking ground and going forward and trying to do these tests for stochastic dominance that's robust to what is causing non-response. So Okay, so I'll just mention here, I'll reiterate some of these objectives for you, but with a bit more detail. So we have a methodological objective, and we have also a novel application in the paper. So methodologically, what we put forward is a statistical test for first order stochastic dominance for ordinal distributions, but this applies to non-response of any form. And the way we go around that is to use the worst case bounds. The worst case bounds that I've illustrated before basically captures all the possible mechanisms that could be causing non-response. That's the virtue of using them. They tend to be wide in practice, but while they are wide in practice, it doesn't preclude their usefulness for comparisons across populations. That's the catch, right? Now, the testing procedure we're using, or developing, pardon me, here, is an adaptation of, I guess, my beloved supervisor's work, Russell Davidson. So with Jean-Yves Duclos, the, I guess, a cabinet minister in Trudeau's government. So basically, they have a paper on testing for first order stochastic dominance under the random sampling assumption, which we're going to adapt for the complex survey sampling setup. And the people who've been working a lot with complex survey sampling, I guess a lot of them are Canadians at the University of Waterloo and Carleton University in that part of Canada. A nice group of people. The theory, the asymptotic theory there is not like how we traditionally think about asymptotics in econometrics. It's different. It's basically sampling from large finite populations. I'm emphasizing this because that's the framework of the paper that we're using, of this paper. And so we're going to use this framework essentially in this paper. We're going to extend it to deal with testing with stochastic dominance and using distributional bounds to go around the issues of missingness. So the application we have in mind, as I've mentioned already, is just this empirical analysis of the dynamics of trust in these Lebanese public institutions leading up to the October 2019 uprising. So I organize an annual meeting in Lebanon called the Lebanese Econometrics Study Group. With Eli Tamer and a whole bunch of other very few, well, there are not so many Lebanese econometricians. But we had to cancel our meeting because of this uprising. But generally speaking, it's just a greater context of how horrible the situation is. We've had 30 years post-civil war in Lebanon of graft, corruption, embezzlement, and it's all financed in some ways by a grand Ponzi scheme, which is now crashing on itself. And so it's quite horrible. You can look it up. And so we thought to talk about, we have data on Lebanon, and data from that part of the world is generally scarce. And so there's an interesting component about this type of application for this reason. So anyways, I'll let you guys Google that if you like to know more about it. So just to, I guess, frame this work with respect to the relevant literature. So, of course, this is not an exhaustive list. So stochastic dominance comparisons of ordinal distributions is not a new concept. It's been around, it's been developed by primarily Allison and Foster in a Journal of Health Economics paper for dealing with the scale independence issue. That's the main, I guess, the main innovation of their work. And it's been extended into all kinds of other areas of study by Dutta and Foster and Jenkins and others. Excuse me. Now, none of that work deals with working with data and the fact that there is sampling. Stochastic dominance tests would be the way to actually test for the significance of these comparisons, right? Because you're only working with a sample, you have and there's sampling variability, you have to carry out a test. And so there is a very large body of literature here, which I will not try to list for you. There's some of it is listed in the paper, but I do encourage you to check out a really awesome book by a friend of mine, senior econometrician by the name of Yun-Jae Wang, who has a book on stochastic dominance testing, a recent one, 2019. It's quite extensive with all the references in that book. Really great book. But so it's just really a lot of work there. But again, like I said, none of these tests really looked at the setup where what if your data was had missingness in it, or due to non-response, or just it's incomplete, how would you carry about the comparisons in that case? So some work in that direction does exist, but the inference is missing, meaning that they've put forward an idea of how to do the comparisons, but they don't really have the theory to back it up. So there's an econometric paper by Blundell, Megir, and others, where they use economic theory to refine bounds on distributions of labor earnings and the studying across gender comparisons. And they use the bounds they use economic theory to refine the bounds. They don't really propose a theory of inference. They allude to ideas about that, but they don't really have anything of that sort. In contrast to this work and that of Lee, who looks at treatment effect bounds, we're looking at a complex survey design, and we have a theory of inference, right? And it's for ordinal variables, right, at this point. So, but missing data and partial identification is an even wider literature, right, that goes back decades. The papers I just mentioned here are the ones that are closest to what is to this paper that I'm talking about today. Now, I'm a great advocate of empirical likelihood. And so the methodology of the paper uses empirical likelihoods and using that in the survey sampling context. And so the papers that in this literature that are close to the ones that are close to this paper are those by Jiahua Chen and Sitter, Changbao Wu and Jian K. Rao. So these are all the folks who are in the Ottawa and I guess Waterloo areas. They're very well established statisticians who developed a lot of empirical likelihood under survey sampling within this large finite population type of design. So that's where this paper really sits in sort of in between these two worlds. And that's what struck up like the interest of econometricians who are nowadays more looking at complex designs and I guess survey designs. Okay. Let me just now start off by setting the stage for you. So in the stage that I have here is that you have an ordinal variable. It's,
hi, Rami.
Hi. Hello.
Yeah, so I have a couple of questions.
Sure, go ahead.
So the Blundell paper, Econometrica, you can use for your empirical application also?
No, because they're looking at quantitative data.
Okay, because you have ordinal stuff.
Yeah, that's right. But they don't have a theory. They don't have a statistical or econometric theory that speaks to the efficacy of their method. They have like a way to compare distributions by looking at the bounds, but they only have, if you look at the appendix of their paper, some very, very selective Monte Carlo simulations, I would say, that says that it seems like it works. It's some evidence about that, sure, but Monte Carlo simulations is not the is not the last say on the validity of these methods, right? So again, they're quite different still, what we do in the paper and what they had set out to do. Over there, they care about comparing income distributions given certain covariates and characteristics. And so they use economic theory to try and refine bounds. We're not doing that here. We're not using economic theory to refine bounds. We're using the worst case bounds, which basically allows for anything that's causing missingness, right? So over there, they want to.
So this is, as you say, this is back to Mansky idea. So
yeah, exactly.
Whatever you cannot.
Exactly.
And also, you said that you'll be doing finite sample asymptotics.
Finite population asymptotics.
Yeah, sorry, finite population. So why is that? So yeah, I know sometimes people derive like this superpopulation stuff, and sometimes.
Right. So why here? Because the complex survey, the asymptotic theory of complex survey sampling is framed in that language. So I'm importing ideas from the statistics literature in developing the asymptotic theory in the work here. So that's because the data are really not IID. So there is clustering, there are stages, there's stratification, there's probability weighted sampling, there's all kinds of stuff that makes it heavily non-IID. And so you have to then account for that in a meaningful way. And the way the literature has progressed in statistics about dealing with those types of sampling methods is to use survey weights, where specifically the design weights of surveys, because the design weights captures all of that structure from the survey's design. And so the asymptotic theory with regards to having design weights buys you a lot of the, I guess, the theory, how to work out the proofs for all of these procedures being valid. Is that?
Okay, thank you.
No problem.
Yeah,
you're welcome. You're welcome. So I'll just start from the beginning. So setting the stage here, we have an ordinal variable that is measured on a numerical scale, whatever it is. The numerical scale, script S, there are k categories, and they're just ordered without loss of generality. So S1 is less than S2, etc., etc. We have two populations because we're going to do distributional comparisons of two populations. And now the way I'm defining this, because it's finite populations. Here, script P, and with the subscript Y indexes the population. It's basically a list of of all the individuals in your population and of what would be their response. What would be their response to the survey? What should they have? Should they participate? And that's what XYI is. And there's a lot of sounds, I guess. And DYI is the indicator variable on whether they respond to the survey or not. So XYI is what is the value they would report should they participate in the survey, or should what it would be. And DYI is just the binary random variable, an indicator on whether individual I in population Y responds to the survey. So in the setup, the practitioner really observes what's described here in the two cases. They would observe essentially the response, should they have participated in the survey, the value that they report. Otherwise, there's a missing value code. It's coded in some way for you as a practitioner to recognize what that is. And so that's what you would essentially see in your data set. Now we're modeling the finite population this way. So capital NY is your population total. When we're thinking about large finite populations, think, for example, of all citizens in Australia who are eligible to vote. That's in the millions, right? That's what I mean by large. In Lebanon, with the Lebanese data, it's all non-incarcerated citizens who are at least 18, I think. Again, that's in the millions. And so the asymptotics covering that is going to be a suitable framework for where we're going with the development of the theory. So let me just put that down here. So first order stochastic dominance in this context now is quite a simple thing to understand. After all, it's a finite population, but large. It just the distribution of interest here, the CDF of the ordinal variable, is just given by the first bullet point. It looks like what you would see for an ECDF, but it's not. It's discrete. It's a discrete population, right? So the CDF is this basically has this particular form. So what then to define stochastic dominance, or what we're after, at least the distributional comparison in this context, we say that population B's ordinal variable distribution strictly stochastic dominates its A counterpart at the first order, strictly if you have these strict inequalities right here. Again, for all categories except the top category, because again, they are CDFs, so in the top category, the CDFs are both equal to 1, right? So you just exclude them from the comparisons. They don't really add anything. And so what we wish to do in this paper is to infer such dominance, right? And this is an important point because it sort of has something to say about how you set up your hypotheses for testing. We're going to get into that a little later, but this is essentially a well understood, I guess, how you should do it. So what we're going to do is try to develop a testing framework to infer this type of stochastic dominance, but using survey data when you have missing values. So we want to infer this type of relationship on objects that are not point identified, right? That's where we're going, right? So just to remind you of all of that. So I was talking about test problems. If you didn't have any missing data.
If there is no missing data, you just calculate those quantities. There is no stochastic component. You just know the numbers.
I'm sorry, could you repeat your question? I didn't quite catch it.
So if there is no missing data, if there is no non-response, you just know all the numbers, no stochasticity, you just compare the two functions.
So this is population right now. What's on this particular slide, it's a large finite population, so it's all discrete. And if you knew all the values of your population, then you just calculate it directly, and there's nothing stochastic, as you say. Indeed. And if you have missingness, then and the survey sample, you must carry out a test to establish such dominance. So let me first of all start off with a more conventional setting where you have the scenario without missing data. So you have, so how would you set up your hypothesis testing problem over there? Because we want to infer that you have dominance, that's what we'd like to infer, you must set it up as your alternative hypothesis. Because if you do not do that, then that means it will be your null hypothesis. Non-rejection of the null is not the same thing as accepting the null, unless type 2 error is really low, right? And these types of tests have all kinds of asymptotic biases, so it's not really the right thing to do from a practical I guess, perspective. You want to set it up as your alternative hypothesis. Now, that's what you would do in bullet point 1 if you didn't have any missing data problems. So this is pretty much the Davidson and Duclos prescription, right? How you would set up your null and alternative hypotheses. Now, what we propose to do is, because what we have is the missing data problem. And so what we're going to do instead is we're going to consider the testing problem given by the second bullet point. Now, let me just mention that the null hypothesis in the first bullet point, I forgot to mention this over here, this guy, this is non-dominance. That means that B does not dominate A. So non-dominance means that basically A would dominate B or they cross. There are two configurations. In H1, there's dominance. The same principle happens with the testing problem we're putting forward, but now we're going to use the distributional bounds to carry out the test to try and infer dominance on the objects that are not point identified. So what we have here is with the upper bound, the upper worst case bound for B and the lower worst case bound for A. Now, this null hypothesis here, H01, just says that those two things either cross or the lower bound of A is bigger than the upper bound of B. The alternative hypothesis in this case, which is the negation of the null, says that the upper bound of B is strictly less than the lower bound of A. That means that essentially the identified sets for distribution B and distribution A are disjoint. They are completely separated and essentially, let me just say very loosely, ordered. Let me just point out how this comes about more, I guess, clearly. So here is, for example, an illustration of the alternative hypothesis with the numerical scale 1, 2, 3, 4, just for illustration purposes. So in this case, distribution B is strictly less than that of A, as you can see. Now, of course, we know the upper bound of B, the upper worst case bound of B is of course going to be bigger than the red line. The lower worst case bound of A is lower than the blue line. So essentially what we're saying is that if you can establish that the upper worst case bound of B is strictly lower than the lower worst case bound of A, then we can basically establish that FB dominates FA strictly at the first order. That's essentially the idea behind the testing framework. And so what this means is what we're really doing essentially is, that's where we're going. Now, I just want to also illustrate what happens with H01. You can have that the bounds cross, right? But the objects of interest are still ordered. And in this case, the worst case bounds are not informative to help you carry out the comparison. They are sufficiently close to each other that would make this a very difficult task or impossible task. And so in the paper, I will not talk about that in detail in this seminar, but I encourage you to look at the paper. You would carry out a sensitivity analysis and see how to refine the bounds using, I guess, very much akin to what I guess the paper by Blundell, McGeer, and others have, but here using ideas of what's causing non-response. So you could do that. But so just to point out that you can still have that the objects of interest are ordered, but you cannot detect that using the bounds. That's what happens when you do not reject the null H01. So it's not the end of the world, of course, if that happens. It just means they're not informative. You can try to find bounds that are more refined or more informative, essentially, to carry out your test. So essentially, yeah, that's it. So what we're doing essentially is we have a rejection event, a rejection of the null hypothesis event, that which is then going to give us H11, and that's going to imply H1 in the testing problem on the first bullet point of 2 slides ago. That's because analytically, what you can show is that the objects of interest here are what have a lot going on in between them, right? They have that the upper bound of B is strictly less than the lower bound of A. And that's essentially how we're going to try and circumvent the making assumptions on non-response by using these bounds in testing. So it's a pretty neat idea, I thought. So anyways, what are these worst case bounds? And this is how I guess you can, this is like the Mansky way of deriving them, I guess. If you want to do that for a particular choice of S, a particular category, what you would do essentially is for deriving the lower bound, you'd have to transform your data for, let's say, XA as such, where basically you don't observe or there's non-response, you put in the biggest numerical value corresponding to the largest category. And with the upper bound, FB, you'd have to transform the data from population B so that when you don't observe, you put in the smallest theoretical value on the numerical scale. And basically, by adjusting your data in this way, very simply, you can then construct these bounds very easily. These are all population, but there, of course, you have a sample analog counterpart to these. They are estimable, right? They are point identified, and you can estimate them and carry out a test as in the null testing problem that we're putting forward. So, okay, this brings us to the setup for the asymptotic theory. I'm not gonna get into super detail here, but I'm gonna give you a flavor of what's going on. So the world we're working in has 2 independent survey samples from potentially different designs, right? You can use different surveys. So in the paper, we're using the Arab Barometer and we're using the World Values Survey. So it doesn't matter what their designs are, whether it's the same survey or not, or if it's a panel. These are 2 independent survey samples. And so with each of these populations, A and B, what do you have in your data set? You have some information that comes in the form of these design weights that I've talked about. So what you have essentially is in the sample, the value of the category, but you will only observe it if DYI is 1, otherwise you don't observe it. And you have then the design weight corresponding to this individual that has been sampled. And this U subscript I is a random subset of these integers. This is how one models essentially the survey sampling by thinking of probability distributions defined on these random subsets of the integers. So you can define a probability space for them and carry out, the standard and technical analyses just within that context, of course. Now, the survey design weights are always reported to you in these kinds of scenarios. So you have access to these guys. They have no missing values. Now, the survey design weight is proportional to the probability of that the individual selected to participate in the survey. That it's a selection probability by the survey designer. Whether they responded or not is what's captured by this variable, right? So by using the survey weights, essentially, we can capture all the characteristics of the survey's design. And that's basically, in a nutshell, what one has to do with these types of data sets. So typically what also arises here is that these survey weights have been scaled so that they sum to the sample size from each population. So the survey weights from population Y are scaled in such a way that they sum to the sample size. And so that usually comes out. It's quite nice. It fits very nicely with our empirical likelihood framework. Now, as we saw with
Can you please give an example of what, like in the application, what are the survey design weights?
Sure. I didn't realize it was you, Igor. Okay. You looked familiar. Sorry, I didn't realize it was you.
Yeah, sorry, I didn't change my name.
No worries. Okay.
Hi.
Hey. So the survey weight is just what comes to you from the survey designer when you download the data set from the Hilda survey or the Arab Barometer. They report what the survey weight is so that you can carry out calculations of, say, CDFs or of means or of medians. It's just a value that is proportional to the probability that the survey designers have picked them to be into your sample. So think about it this way. The survey designers have the list of all individuals in their population. They have to then decide which subset of these they're going to pick, right? And they have they have their multi-stage clustering stratification methodology that does that. What they report is the probability of the individual being selected into your sample, and that comes in the form of the survey weight. You don't know the joint probability of 2 individuals in your sample. They don't report that. Sometimes they do, depending on your level of access. But what happens is you get that value because that's what you need to develop a consistent estimator using the Hayek empirical CDF, for example. You will need that type of survey information. So there is a design effect due to that. Does that?
So is it right to think that if a designer wants to have 60% of female and 40% of male, then my weight would be 40%?
Sure. So they have, in designing their survey, they have various goals, as you point out. And so if you wanted to then, do inference, so I guess confidence intervals or testing, you would have to then use the survey weight to reflect the nature of the sampling. And that's essentially the input that's going to allow you to carry out your large finite population asymptotics. So you need that information. Otherwise, you can't really do anything with it. So, but a lot of these survey designers, they report these weights. They also have the habit of reporting all kinds of other weights with their packages that people might want to use. So I know in Australia with the Hilda data set, they report, for example, what they call population weights. They're adjustments of the design weights to reflect what would be the population, right? So, but whether that's a good thing to use or a bad thing, that's still very debatable, I think. So anyways, but they have this habit of doing that, which I think is not a bad thing. It's just you have to be really careful about what to use. And here I'm emphasizing you need the design weight because that's the information from the survey that you need in carrying out the construction of your estimation and tests. Without that, you can't really do anything in the face of this non-random sampling scenario.
Yeah, and design weight depends on the.
So the design weight is something that comes
Okay,
from.
so in the IID sample, it would be just ones.
And yeah, exactly. They're like ones. Yeah,
right.
they're exactly. They're all ones. But the design weight is there to reflect your weight in the sample. But your weight in the sample also reflected in the chances of you being selected into the sample, like inverse probability weighting.
Okay.
Think of it that way. That's another way of thinking about it. That's roughly how they design these estimation methods in the survey sampling literature.
But Rami, this is additional information, and that information is not yet, it has to change the bounds that you use.
Sure.
You're not using it yet, right? It's like a stratified sampling. You have probabilities of being in a strata, which you can use as inverse sampling, inverse probability weighting estimation, which will give more information to whatever you're estimating using that sample. So you'd be more precise, and consequently, you should be able to do more, a smaller, tighter bounds, I suppose.
Sure.
So that's question one. The other question is, though, if there is this indicator of a strata which is a function of W, then you can use conditional probabilities based on that W, which brings you into the area of ignorable selection versus selection that's completely at random. And there again, you would have some different, completely different story, right? Because you now can you don't need the bounds. You now have you can now estimate the objects using weights, using those weights.
Well, well, yes and no. I think about using ignoring the bounds. So you see, think about like the setup that Rustam was talking about earlier. If you have systematic missingness of the rich, and you want to talk about inequality, which of course naturally involves the rich and the poor, and you only have your non-rich people in your sample, reweighting is not going to do anything. It's not going to help you at all. So you still need to use bounds in that sense. So unless you're willing to say that,
but you know your W tells you how many reach we don't have, more or less.
To some extent, it is, yeah. To some extent, it'll give you that, but it's still the sampling with the missingness. It's not really ignorable, I would say. Even though you have information from the W's, that's just going to really help you design a survey-weighted empirical CDF, right? That's really its role operationally in inference. So instead of having IID empirical CDF, you have a survey-weighted one. But because of missingness, you have to have a survey-weighted estimator of the bounds, right? So
survey-weighted estimator, yeah. So I guess I'm not seeing how you use W at the moment.
Right. It's all survey-weighted. That's essentially where we're going with it. That's how you capture the information from the survey's design, right? So, but it has all of these flavors of like inverse probability weighting and all these other ways to think about it. But here I'm just using them to do survey-weighted estimation and inference.
Okay.
Yeah. Okay, no problem.
But
so
can we think, to simplify stuff, can we just think about what you're doing? Suppose that there is like IID data, so all weights are 1, you still have a problem of non-response.
That's correct.
So you still need to do some analysis. So
that's correct,
like
yes.
The simplest application would be just forgetting about these weights, thinking 1-1.
Exactly, absolutely, spot on, yeah. So the weights, are just there to capture the effect of the survey's design, nothing more than that. Yeah. Yes.
A related question, Rami, these problems would arise exactly because of dependence, because of multi-stage design, I suppose.
So with the multiple stages or the clustering and so on, if you don't have the survey design weights, And so what you would do is just use the empirical versions. It's going to just lead to biased estimates, right? That's where the issue arises if you don't have the survey weights. But because these survey designers want their people to use their data releases and their data sets, they provide these weights, of course, and it's for efficiency and avoiding misspecification issues, one should use them in practice. And so this is what makes it, that's what makes it different than the standard classical setup where the weights are all one. So as Igor was saying, indeed, if the weights were all one, that just puts you into the classical econometric setup that we all know with IID sampling.
And considering dependent structures, I understand clustering is natural. How about special dependence? Does one have it in complex surveys or ordinary surveys?
Oh, special dependence. I don't see why not, because you see what they do is they create major statistical areas. Those are geographical areas. And then they have to weight how they sample from those places, right? And so you would think that there is going to be dependence across the different regions. And so that would introduce some sort of spatial dependence, I think, when you're thinking about the data frame, right? The areas that they're going to sample from and how they break it down in stages and clusters and so on and so forth. So absolutely, there is all this dependence that is in the sample. And the way we accommodate it is through the survey weight.
Mm-hmm. Thank you.
Oh, no problem.
Rami, I have to hasten you a little bit because it is the top of the hour, and we're not yet half through.
Sure. I'll pick it up. Sure. So essentially, what we're doing here then, on the level of the sample, is we have to basically how we develop the bounds by adjusting the population values based on the values of DI. You do the same thing with your sample, very much like what's going on over here. You just put in the smallest theoretical value where it's missing for population B, and you put the biggest one for population A. And that allows you then to get to the estimators of the bounds, like the Hayek empirical estimators. Now, with our testing framework, we're using something called pseudo-empirical likelihood. The word pseudo comes from the fact that we don't have an actual likelihood. It's a survey-weighted likelihood. So this is like the empirical likelihood objective function, just it's survey-weighted. And so what happens then is you want to impose that the probabilities you are selecting on the two samples, which are these pi with superscript y's, they have to sum to 1, which is this part. They have to be strictly positive. And then you want to impose this equality constraint. Now, why are we imposing that the two CDFs, we start off with just one S, and we do this for all the S's, for all the categories. We want to find the likelihood from imposing this restriction. Why? Because the boundary of the null hypothesis is where at least one of the CDFs are equal at least 1 point. And so what we're doing is we're imposing being on the boundary of the null at each S, and then we're going to maximize by over all of them. So, or actually maximize, which will then end up giving you the minimal ELR statistic. And so here's how I'm using the survey weights, Artem, so that you can see it's right here. It's all survey weighted, right? So this is just the moment function for stochastic dominance down there, the difference of the two indicators. So this is just like EL, but with survey weights. So what we do is we solve this problem for each S, and then what you want to do is denote, take the maximal values, LRS, call them that, and then you want to calculate the unconstrained estimators of the CDFs, which is just the Hayek empirical estimators using the survey weights as given on this slide, which gives you the unrestricted pseudo-empirical likelihood value or unconstrained one. And as with empirical likelihood and its variance, what you want to do is define the ELR, the pseudo-empirical likelihood ratio statistic for testing H01 is that it's the minimum of these values. And you would calculate the minimum only if you observe dominance in the sample, right? If you observe dominance in the sample, then you test. Otherwise, if they cross in the sample, that's basically evidence for the null. And so you associate a 0 value for this likelihood. This is essentially what the testing framework of Russell Davidson and Jean-Yves Duclos, but now adapted here with survey weights from like what Chen and Sitter do, but we also introduced the distributional bounds. And so the decision rule is to reject the null hypothesis if and only if the statistic exceeds a critical value, which under some conditions ends up being a 1 minus alpha quantile from the chi-squared distribution of 1 degree of freedom. Here I say some conditions because there's something called the design effect, which would factor into the distribution, which is then a quantity that comes from the survey design essentially. But we have normalized that quantity for simplicity. In the paper, I discussed that in great detail. So if you want to look at it there, but it doesn't really change much of the analysis so long as you account for it. And so the asymptotic construction under the null hypothesis is as follows. Basically, all your randomness is due to sampling schemes from the surveys, right? So that's where it all comes from. And the way we're going to think about large finite populations here is as follows. You would think of, now here I denote script M as M for model and P for population, P is for population. So I'm collecting into my model all the populations which are basically lists of size ny, basically of xyi and dyi, what those values are. And the basically that's basically my model, all the different finite populations that you could have, right? All the combinations of xyi and dyi. And so we're going to denote a particular population in this model by a capital pi here, capital pi over here. And so the true population is going to have a subscript 0 on it. And so all finite populations are basically all of this particular form. So it's just these lists of what each of these individuals and these populations would say, and whether they would respond to the survey. And so the model of the null hypothesis just captures all those finite populations for which the restriction of the null is true. Now, that's what it is. And you're basically looking at randomness being subsets of this population, random subsets of the integers indexing the population values. That's how you would think about the asymptotic theory. So in this setting, pi 0 is now satisfies the restriction of the null if it's an element of this model of the null hypothesis. And we're interested in looking at the size of the test, which is now here, the supremum of the rejection probability of using the testing procedure, where here, this is not conditioning. In the survey sampling literature, they use this bar as to indicate that data is drawn from population pi. So because you're taking the supremum over all the different populations you have, but what is random here is essentially the different samples that are possible from the survey's design, from the survey's scheme. So for different populations, you can then draw the samples and calculate these rejection probabilities. And you're looking then, the size of the test is the maximum or the supremum of those. Now, what we're going to do is approximate test size using an asymptotic version of this, where the population totals get very large. And so here, essentially, in the paper, I don't want to introduce these assumption here. It's a very long assumption with a lot of technical details. You would introduce a lot of structure on the model. You would embed it into a sequence so that you can essentially have enough structure on it to give rise to having asymptotically correct level, where the asymptotics is with respect to the population totals. And so these restrictions that are used are quite standard and are a combination of restrictions or assumptions that come from the survey sampling literature and the partial identification literature. So a clever combination of the two would buy you this result. And so you can look it up in the paper. It's quite technical. I don't think there's enough time to go over that here, but I'm happy to talk to you about it further afterwards if you like. So we also have a construction, let me just put it here, under the alternative hypothesis, where you would collect the model of the alternative are all the populations where you satisfy now the restriction of the alternative. We have theoretical results on local power local asymptotic power. And again, basically where you have distant local and non-local alternatives, where we can show that for particular sequences of finite populations, you have power 1 in the limit, but sadly, I guess more generally also why sadly, a lot of these tests are asymptotically biased against certain directions. And so I detail what those are in the paper, but you do have that. It's just a feature of these types of tests in general in this literature. So we can talk about that later if you guys wish, but I think in the interest of getting through the seminar, I'll defer to a discussion later on about it. So here, I will now reach the application. So the data that we have is essentially trust level data in Lebanese public institutions in the run-up to October 2019, where they had the mass protests. So we have data in the years 2013, 16, and 18. In 13, we used the World Values Survey, and in 16 and 18, we used the Arab Barometer. The reason why we used two different surveys is because the question that is of interest to us, well, how much do you trust your government, for example, was not posed by the Arab Barometer in an earlier wave. And so we wanted to look at what happens in the run-up from 2013 onwards. And that's why we have different surveys in our empirical application. So both surveys are nationally representative, and you have data on various public institutions like the Lebanese courts, government, parliament. Political parties is not a public institution, but it's there, and you have police force. So with the trust level data that you have here with the surveys has the 4 categories, not at all, not very much, a lot, and a great deal, like we saw earlier. And we, in the paper, imposed the numerical scale 1, 2, 3, 4 without loss of generality. And so the target population here are the non-institutionalized Lebanese citizens aged 18 and above. And the population totals in this case are in the millions. And so the large finite population asymptotics seems to marry well with this type of application. And so the data set sizes are reported here are in the thousands. Essentially, there are some subsamples that we have accounted for. And what we're after is essentially the following. We want to see if there is a way to infer the following chain of inequalities. We're going to use the test I introduced before as a building block in constructing this chain using a union intersection testing procedure. And so this is evidence to say that if indeed this chain holds, you can say that trust levels have been diminishing over time, right? From 13 to 16 to 18. That's why the chain is interesting. As you will see later on with the data, it's, we have some negative and some positive results about that. So let me just clear my screen here. And so here are the estimates of non-response from these different years for the different institutions. As you can see, the government one is very large. You have then stuff in the 4%, the 7%, 6%. Some of these are quite low. And the non-response rates declined with this Arab Barometer, right? It's with the World Values Survey where things are wishy-washy with them. So where non-response rates are high. And so it's important to account for the fact that you have this type of non-response in comparing distributions of this sort. And so we're going to consider this intersection union procedure to carry out inference for the chain. And of course, the test we introduced is a building block in doing that and I'll show you in a moment. So the testing problem is now that here, 13 does not dominate 16 and 16 does not dominate 18. The negation of that is just essentially the chain, right? The negation with the or logically implies that. And so this is why it's why we set up the problem this way. So in the application, of course, we have to use the testing procedure we set out to break down the intersection union test into subtests, I guess. That's another way of putting it very loosely, because you'd have 2 sub-hypotheses now in the null, which is in the union form. And so you can build a test statistic by the minimum of the 2 LR statistics. And this accounts for multiple testing and is invariant to a Bonferroni correction, you name it. It handles that all, takes care of it. And so what happens then is you have your decision rule, it turns out also that you want to use the critical value from the chi-squared with 1 degree of freedom distribution. And so you would reject this null hypothesis if your overall LR statistic now exceeds that critical value. And so it's a simple extension of the results that we talked about earlier. And so what do we find? So here I report the realized values of the test statistics and decisions based on a 5% significance level. So H2 is now the overall null with a chain. We do not reject because they're all 0. What happens is that some of these bounds are crossing, especially between 16 and 18, the years 16 and 18. However, with H21, between the years 13 and 16, they are not crossing. So they are actually ordered. And you can get the realized values of the LR statistics that are reported here. In fact, some of these are significant at the 1% level, right? So what you see here is that we can't really tell from the data whether overall I guess trust levels have been declining over time, but they've been sort of declining from 13 to 16. But what's happening after that, the bounds are not really informative in helping us figure that out. And so here's an illustration of what we're actually observing as an example with governments. You see here the black line is for the worst case upper bound for 13, and the dotted line in this left panel is the 2016 counterpart for the lower bound. The black line is always below the dotted line, and so you would carry out the test. This is in contrast to what happens in the other panel, where you see that the black line crosses the dotted line, where the black line here is the CDF of worst case upper bound for 16, and the dotted line is for 18, but the lower bound. And so here the test would not be carried out for the sub-hypothesis. And that's why the minimum of 0 and something else is just something positive is just 0. So essentially here for the overall chain, the bounds are not really informative, but we did find some very strong evidence that between 13 and 16, that there has been a decline in confidence. And this was, I think, around one of the election dates for parliament in Lebanon. So the results we find is they're quite strong in the sense that they're invariant to a numerical scale, and they're invariant to the nature of non-response, the non-response mechanism for the results between 13 and 16. And they're significant at the 1% level. And so that's quite nice, I think, from an empirical point of view, because also the test is conservative, right? So this is really strong evidence when you reject the null. And so essentially, that's the bottom line with these findings. So in conclusion, I will just restate very briefly here that we set out to develop a testing procedure to infer a strict stochastic dominance ordering on the basis of 2 independent survey samples with non-responsive of any kind. Those objects are, of course, not identified on the account of non-response. And so developing a way to do the comparison to establish such an ordering, one has to use bounds. And so the idea is that we have set up a testing problem where the rejection event implies the ordering, right? The rejection event involving the comparison of the bounds appropriately does that. Now, if one fails to reject the null, unfortunately, you cannot conclude anything informative about the ranking of the distributions. As I illustrated, the partially identified distributions can still be ordered, but the bounds are so close to each other that you cannot really tell because they cross in the sample. And so what you can do, as I talk more about this in the paper, is that you carry out a sensitivity analysis. You could refine the bounds by introducing, say, assumptions that are plausible in practice, like dominant selection or monotone selection. And that can help you refine the bounds so that you can carry out the test using these new bounds. But again, these are under assumptions, of course, of that sort. So it's, you have to, that's just the nature of the practice. It's not going as far as imputation, but, you have to make some sort of an assumption if you want to study the sensitivity of your outcomes, empirical outcomes to these types of assumptions. That's the virtue of it, I would say, because you connect the outcome, that empirical outcome with an assumption. And so you can then make up your mind what you think is actually at play. So I think that's pretty much it. Thanks.
Okay, thank you, Rami. Any questions for Rami?
There's something in the chat. So
Rami, I sent the link to our paper with Anton and Paul. We dealt with robust inference on comparison of inequality measures using T-statistics and group estimators.
Okay.
And there is a paper by Data and Zhu that shows that these approaches should work under missing data. So essentially, there is no need to estimate standard errors consistently. That question on special dependence was related to the analysis in the updated version. In the paper, the methods appear to perform well under different types of dependence, like special, clustered, in general, T-statistic approaches. There one doesn't estimate standard errors or limiting variance consistently. Just look into group estimates also appear to perform well. Maybe that may be of interest.
Sure.
It's interesting what kind of dependence settings in complex settings would be the most appropriate, coming back to that question. Clustered, I suppose.
So the one that I'm most familiar with is what happens with in Australia, the survey called HILDA in Australia, the Household Income Labor Survey. And over there, it's a household survey. And it has various stages. And the first stage is to define like major statistical regions. And then they have to think about how much weight they would put on each of these regions when they want to sample from the different regions, and then within each region, how they sample across a more refined frame. It goes down all the way to, I guess, districts and housing blocks even. And so there is a lot of that's going on with the spatial dependence for sure. This is, I mean, the particular forms, I guess you'd have to read how they constructed their survey to get a sense of what's happening with the spatial dependence, but it definitely is an issue there. Like they also make sure that they sample more in regions which are less densely populated than, let's say, cosmopolitan areas. Like
and I understand that ensuring unbiasedness for different groups is important. Maybe if one considers comparisons of the parameters, there will be cancellations under the null, and that may help. But
I guess that could be a way to think about that. I mean, to go about it. But I have to look more deeply at your paper and to get a better sense of.
We would be grateful for any comments.
Yeah, sure. And so
maybe in applications to stochastic dominance, one would estimate the CDFs for groups and then consider differences or different integrals of this empirical CDFs.
Yeah, sure. That would be definitely very interesting in practice. So it's still, I think, a fertile area of research. Not much is not many people have looked at these distributional comparisons in light of missing data. There's very few papers, if any, that have thought about this, but they're predominantly take the imputation approach, which I'm not really a proponent of. So,
one interesting extension, it seems, thinking about joint distributions and copulas, maybe multidimensional inequality. So then we need to work with multivariate CDFs.
Sure. So there is a notion of ordering multivariate distributions using, I think, what's called multivariable stochastic dominance. That's been used in multidimensional poverty analysis. So over there, again, you have missing data, but the problem there is more complex because of the dependence as well. So it's very I have not looked at it yet, but that's something that I'm quite interested to think more about. I've been looking more recently at missing data with dependence also, with copulas, but that's like a separate, I guess, line of research, different than doing distributional comparisons. Although a lot of these dependence measures are inherently orderings, like Kendall's tau is one of those things, but in quadrant dependence. But over there, the problem is more subtle because you're looking at the issue of dependence rather than looking at the ordering itself.
And holding fresh then would be useful. And also, since you mentioned different types of dependence and refinement of those, say, under positive concordance or positive order dependence, one can just bound by the products, I suppose.
Oh, sure, sure. Indeed, if you are willing to believe in that dependence structures are bounded by these types of copulae, then that exhibit these, I guess, let me see, let me rephrase. You could bound the dependent structure that way if you think it's plausible to do so, sure. But that's then information that's input from the user. And, you can still study the outcome of that as well. As you could change these assumptions, which then creates that sensitivity analysis type of, setting to connect outcomes with assumptions. This is what's really nice about the partial identification framework in econometrics.
Thank you.
Oh, you're welcome. I guess I'll revert back to the, let me see how we're going to do that. I can't go back to my screen. I guess you see Rustam's paper on my screen, but I have to see how to get out of here. Then maybe if I stop sharing and, oh, I see.
No, we see your thank you slides.
Oh, you see my thank you slide. Oh, okay, thanks. Okay, thank you. Sorry, I thought that for some reason you saw Rustam's paper, but it looks like a really cool paper. So I should read it. So,
I would like to clarify, Rami.
Sure.
Yeah, Igor, go ahead. I just want to make sure that we have PT on Rami. It's 11 p.m. in where we are. So yeah, go ahead. I just might need to excuse myself, but we see Rami. I see Rami from time to time, so I'll have my questions when I see him. But good seeing you, Rami.
Yeah, thank you for the invitation.
Please carry on. I just have to, I guess, say goodbye for now.
Sure. Have a good night.
Take care. Nice talk. Thanks, Rami.
Thank you very much. So let me see if I can go back to my slides. Excuse me. Let's see if I do that. No, that didn't work either. Let me stop sharing and resharing, I guess. That might change things a bit. And if I now share my screen, yeah, perfect. Okay, yeah, here we are. Just in case you wanted to refer to something on the slides, that's the reason why I went back here. Go ahead, Igor.
Yeah, so first of all, I would like to clarify. So you build on Russell-Davidson papers by allowing non-responsiveness and doing bounds, and he does not allow. But in his paper, they use also empirical likelihood stuff.
Correct.
Okay, so the contribution is this, and then you have this clever idea that you can say, okay, we don't have any information about non-response, so we just agnostic without any assumptions, and the clever stuff is to rearrange, to put like in one category to the left and then the other to the right, so that you have stochastic domains without knowing anything. Okay, yes. This is great, really great. And now you say that you're also doing in the appendix a sensitivity analysis, and I'm wondering, like, what would be like one example of the assumptions you can introduce and how easily you can introduce, because as I see what you're doing, like in the main text, is this mechanical rearranging which is very clever and which gives you like really good result without assuming stuff.
Oh, sure.
Now, if you have additional information, is it easy to add it?
Absolutely, absolutely. Let me just point to you in the paper where that is. So let me just stop sharing for a moment to just set up the paper. Just I have it here. Give me just 1 sec. No, that's not it. That's not it. Here it is. Okay, so let me just share my screen with you now here. So this is my paper. It's also been very recently accepted at Journal of Econometrics. So these are all these assumptions, as you can see, quite technical. There is a section about using these bounds in this discussion section 6. So here is one example where you have essentially, so you have, pardon me. Okay, so you have the two populations, but you might think that the one that is conditional non-response dominates its response counterpart. And so when you go to the law of total probability expansion, you can then bound it using the conditional distribution, conditional on response. So then you can refine the bound that way. And when you do that, you can introduce a new testing problem involving the refinements. And so that would be what's in 6.2 here, where you now have a refinement of the bounds, and you can then carry out the test. The catch is that by imposing these refinements, you're going to introduce nuisance parameters that are, of course, estimable at particular rates. And so, then the asymptotic analysis in the paper must be extended to those frameworks, because of course, depending on how quickly these nuisance parameters converge, that can impact the distribution theory. And so I just mentioned these things here into some detail, how to go, what happens there. But I do give two clear examples of how you can introduce these plausible assumptions on non-response, like dominant selection here. And this example too comes from Mansky, where he wants to bound the, I guess this is called a propensity score. So where you can bound the propensity score as being in the neighborhood of missing completely at random. So you can define a neighborhood in which you can look at non-response mechanisms that are in the neighborhood of missing completely at random in a particular way. And then you can do all your analysis conditional upon that, right? You can then deduce what the new bounds will be, the refined ones, and then introduce a new testing problem based on those refined bounds and carry out the test. But I'll predicate or underscore, let me say, that you will introduce nuisance parameters that need to be estimated. So in principle, there shouldn't really be an issue if you account for that properly. So I can send you the link to my paper if you wish also.
Yeah.
And one other thing, in the empirical illustration, we have a section on the sensitivity analysis. So you can also look at it there, how we impose it and how we work to illustrate between 13 and 16, the 2 different years, where we can develop the sensitivity analysis to impose these new bounds that come from the assumptions on missingness that are plausible. And then you can re-carry out the test, and you can get, there's a discussion about that here. It is all definitely doable, as I illustrate in the paper, but I just didn't have time to talk about it today. Well, tonight in my case, so in my time zone.
Yeah.
But happy to talk more about it.
Experience. So from your experience, what is easier, to work with discrete outcomes or continuous outcome in this type of problems?
Oh, wow.
I'm asking because I've seen, and actually I have a paper in a completely different setup when for some reason you want like to jump from discrete by smoothing stuff to continuous CDFs and then do the analysis. Do you have any experience, intuition?
I think that I mean, I've seen these types of transformations that you're talking about, going from discrete to continuous. Sometimes when, especially in bootstrapping, when you want to smooth the bootstrap, as they say. I've seen this like with Peter Hall's work. That's been the extent of where I've seen that. But I guess I would say discrete objects are far simpler than continuous ones.
True.
Because you just don't have tails. So that's really the main thing you get out of it. But I think more importantly, it's whether it's appropriate for if that structure is appropriate for the setup that you're working in. So with categorical data, I mean, it's just what it is. It's just defined that way. But I've seen, for example, other settings where people discretize data, like they discretize continuous data, but I didn't really register why they do that to begin with, because it sounds like they're throwing away information. And so I guess, but that's the limit to what I've seen. But I would.
So for empirical likelihood methods, it's not a problem to have discrete versus continuous.
Right. It's versatile. It's just its modus operandi is discrete parametric, but its asymptotic theory is non-parametric, I guess.
Yeah.
But I would think the best way to think about this is what's the situation you're in regarding the setup that is pertinent, right? Whether the data should be continuous, like in the case with income distributions. I guess if you are censoring data points to make things discrete into groups, I know that, that reminds me of something. A lot of data, especially from many years ago, that was made like publicly available was discretized like that. So this sometimes does arise in practice. I think even the current population survey in the US still practices this, where they might censor income values to intervals. So they discretize things that way, and that then is throwing out information, essentially, for the practitioner. If that's what you're stuck with, then that's what you're stuck with, right? But it does happen on the side of survey designers. But people actively, practitioners discretizing the data themselves, I have not really seen that. And whether that's beneficial, I would think it's the opposite. You're throwing out information.
Yeah, and also I think in survey you may have some baseline information, or you don't have some individual characteristics.
Oh, so yes. So it depends. Like from my experience with the Australian survey data, they actually want to estimate non-response and study what is causing non-response with characteristics they have. For example, when they design their survey, they have household characteristics. Like they know, for example, a household in this particular neighborhood has, say, a median weekly income of a certain quantity. So you know which neighborhoods are richer ones and which ones are poor ones. And then they use this in, say, a survey-weighted logit model to try and predict outcome, non-response. So they build a non-response model to see what's going on, to understand non-response. But again, over there, while the idea is, I think, well-founded to try and understand non-response, a logit specification is a specific parametric one, and there is a lot of structure in that which can be misspecified, right? And so I don't know how believable the results are there, but they do find things that make sense, right? That you would think logically makes sense. Like richer households are more likely to not respond. They're in gated communities and they are reporting their incomes or information about them. They're more sensitive about that. And so it's less likely that they would participate. And so you would think that something like monotone selection makes sense. Like the richer a household is, the more likely they are to not participate in a survey, right? But if you discretize income, it's going to make estimating these things even harder, right? Because if you need to have information that is more refined to understand monotone selection, like at different income brackets or levels, then the task of doing so is much harder with income that has been discretized. You can only say something about what happens at the boundaries of those brackets. Then. You can't say anything about what happens in the middle.
So in the Lebanese data, you don't have these characteristics.
So we don't look at income data, of course, in this paper. I think they do have surveys about income, and they do report raw values, but we're not looking at income data. It's just categorical what we're doing here. So it's just 4 categories, and
Right.
So it's just discrete by construction.
Yeah. So do you have any idea how to include this additional data? So at the moment, you just discard all these individual characteristics.
Sure.
Any idea how to make use of it?
Oh,
to
sure.
improve
So
the bounds.
Sure.
Even if you don't want really to model non-response in like logit or parametric form, stay where you stay, okay, agnostic, but still you have some data.
Yeah, sure. I mean, you can try to do that, but I think it's inescapable that you have to put some structure on non-response to do so. You just can't. Like, for example, there's nothing stopping me from building a logistic regression model for non-response with all these extra characteristics, like which neighborhood people live in, if they're affiliated with a political party, or, all these characteristics. You could do this, but the analysis is then hinges upon that assumption, right? And you can carry this out in a sensitivity analysis. And in fact, I particularly support doing a sensitivity analysis, but of course with plausible assumptions. Now, whether the logistic regression approach makes sense, sure. Whether it doesn't, that's a subject of discussion between people who know something about non-response, like the survey designers, I guess. But you could do this if you think it's what is at play. In fact, it's a simple parametric way to impose things like monotone sample selectivity. You can put restrictions on parameters that they're all positive, right? And so that then you have, or negative, like there's like negative selection into the sample, right? Or into response. So you could do things like that. There's nothing, and you could incorporate that here. I just didn't go into that level of detail with these characteristics. I decided instead to just work with without those characteristics. But by all means, yeah, an extension would involve using these characteristics, and I didn't discuss that in the paper. But you're absolutely right. It's that's something worthwhile doing, but not in this paper, I think.
Thanks. Thank you very much.
Oh, you're welcome, Igor. I see that there are 2 questions in the chat here from Rustam. I think, yeah, this is that the, yeah, I see here.
Yeah, I just posted references that came to mind. So one of is on bounds on copulas, including dependent structures. Concerning missing data, this second paper, Yulong has presented it on inference on tail indices that may be conducted only income shares.
Oh, yeah. Okay. Yes. I don't know the paper, but I know Alexis, the co-author of Yulong. So it's so I know that they've been working with tail dependence and these exponents from top income shares. He works with them, but I don't know. Thank you for the links to these papers. I'll have to look at them.
Yeah, they use the Stochastic approach as well, since the number of observations is unknown for groups.
Okay, it looks very interesting. I don't know them, but I'm happy to discuss these with you after I've read them. So I just don't know what to say about them. But they look.
Thank you very much.
No, thank you. No, thank you for
a very interesting talk.
Oh,
colleagues, if there are any other questions. Thank you very much, Rami. It would be great to continue discussing research and.
Oh, sure. Look forward to it. I'll read them up and follow up with you. The very interesting questions. Thank you very much for the questions and the feedback. It was also nice to reconnect with some people also that I have not seen in a while. So thank you also for inviting me. So,
thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Bye-bye.
Yeah. Bye.
So I guess I will. I guess I will leave. I think, is that how it works?
Yeah. I
Yeah,
can
it was great
stop,
to see you, Rami. Thank you very much.
Hey, nice to see you too, Igor. By the way, where are you these days?
So I'm in Moscow, HEC Moscow.
Oh, okay, cool. Well, I hope to one day come through Russia again, and maybe we'll go out for a drink at some point. Or if you come down to Australia, let me know.
Yeah, let me know. Let me know if you're around. That would be fantastic.
Yeah. Yes, we'll do. I wish you all a good rest of your day, and thank you again for inviting me. So have a good one.
Thanks for great.
thank you very much.
You're welcome.
Good to see
Ciao.
you.
Good to see you. Bye.
Vamos